All righty. There we go. That should do it. So we are now recording. So just a couple quick things. Firstly, speaking of recordings, the first meeting that we had that was being recorded, which was last Friday, that is now available on YouTube. I threw the link in a new content folder up on Blackboard. The content folder is just called Links to Class Meetings. So if you're ever absent, if you ever want to refer back to a class meeting that we had, feel free to just go on Blackboard, go to that folder, and you can find everything there. It's all dated for you as well. So last Friday was 129, and you'll see class meeting 1-29 there. Okay, pretty itemized, pretty easy. Secondly, so I got two emails regarding just a quick explanation that I need to give. Either I gave it before and I just didn't explain it well, or I totally forgot, which is absolutely totally plausible. I was asked what the dates mean next to the lecture videos on like the links on Blackboard. So if you looked at the most recent one said, like lecture 2, and then next to it said, 2-1, right? The date next to it is going to be the date that we discuss that lecture and its accompanying homework. So basically what it means is you just have to watch the lecture video before that date and obviously try the homeworks and whatnot before that date, just so you're prepared to, come into class with questions or, answers. So, again, today is February 1st, which is why it said lecture 2-1. The next one, which will be up today, is going to say lecture 3, 2-3. Okay, so if anybody has any questions on that, feel free to ask me, but hopefully now should be a little more self-explanatory. Okay, there's also a reminder. Today is going to be the first day of office hours. And as we agreed upon as a class, we're going to be doing office hours Monday and Tuesday. I still didn't fix the syllabus, but I will fix it today. So office hours today and office hours tomorrow. Feel free to stop by. I know it's the beginning of the semester, so, I don't anticipate too many questions, but if you do have questions, feel free to come by, ask what you need to, get whatever help that, you need to get. Also, with that being said, I realized that I didn't send out a meeting invitation for the office hours. So you will all be receiving probably another email just saying that there is now another meeting scheduled at 4:15 today, and then again 4:15 tomorrow. Yes, Chris.
This isn't really having anything to do with the class, but I do play around with calculus and derivatives because I know I have to take that class again. And sometimes I get a little hung up. Are you really good with calculus? And do you mind me asking you once in a while? I mean, if you're busy, I'm not going to ask you.
Yeah, we can definitely discuss that outside of class. I'm fine with calculus, but that's something that we can talk about more after class or during other time. But yeah, absolutely.
Thank you very much. I appreciate that.
Yep. Okay. Any questions on where to find the class meetings, on what the date means next to the lecture videos, or when office hours are? Just want to make sure we're all good with that information.
Will there be lectures posted for Fridays as well, or are Fridays just going to be like the quizzes and stuff?
Yes. So there's going to be the general format is there's going to be a lecture posted Friday that you watch before Monday, one posted Monday that you watch before Wednesday, and one posted Wednesday that you watch before Friday. So there's going to be 3 lectures per week, and because we have 3 classes a week. Yes, Erin.
So lectures are not done during class time. We watch them on our own time.
Yes. Yep.
Okay.
We discussed this during the syllabus day and also the following day. The lectures are this is just what I found to be the most flexible and the most beneficial to students. So the lectures are done on your own time, and we discuss the homeworks, questions, and also we extrapolate upon the lectures during these meetings. That's correct.
All right. Thank you.
Yep. Any other questions with that? There's one last topic I just want to get through before we get to the homework for today and the other questions. Okay. So I received, again, 2 emails asking me why I don't collect homework. Now, again, this is Math 104. It's one of the lower level math classes, and I understand that you might be accustomed to professors just always collecting homework, always taking it from you, and making it part of your grade. There's 2 main reasons that I don't do this. So, firstly, the main reason that I don't do this is that it's your first attempt at new material. Whenever you try homework that goes along with a lecture or a new lecture or whatnot, I have to assume it's your very first time seeing it. Now, for many of you, and especially with the introductory material that we're doing right now, you've probably seen this before, but it has to be my assumption that you haven't seen it before. And that assumption has to carry the entire rest of the way through the class as well, through the rest of the semester. So because I'm assuming that you've never seen this before, I feel like it's very unfair for me to grade you on your first attempt ever at trying this new material. Think about all the first times that you've, done anything for the first time, whether it's, riding a bike or whatnot, swimming. How good were you at your very first time, right? When the first time that I tried making chicken parm, I burnt the hell out of it. So, if somebody was grading that, I would have absolutely gotten an F. So, my idea here is I think it's unfair to grade you on your first attempt at doing this math. The second thing is you might also be wondering, why wouldn't I just grade you on completion then? And I feel like completion or grading based on completion doesn't necessarily encourage you to, learn the material. It only encourages you to just jot things down and hope that it's good enough to be considered completed. So I don't like to do that either. And again, this leads me into the next main point, which I know we discussed before, but the quizzes are based on the homework questions. In fact, some of the quizzes just have homework questions directly pulled out of the homework, like copy pasted verbatim. There's going to be times where I change some of the numbers around. There's going to be times where I change some of the orders of operations around. So it's not exactly the homework, but if you understand the homework, and even if you don't understand the homework, if you come into class and you ask, what you need to ask about the homework so that you can gain a better understanding about it, everybody has the ability to just ace the quizzes because, again, it's directly coming from there. So why don't I collect the homework? It's because you are all going to be essentially quizzed on the homework anyway at the end of each week. Okay. Anybody have any questions on that? Okay, cool. So I'm going to go ahead and start sharing my screen, and we can go ahead and get started. So the most recent lecture that we did, this was following some topics like sets. So we were talking about union and intersection of sets. We also were discussing, the proper way to handle complex fractions. Some of this stuff was on your preliminary exam. So hopefully if you had questions on that, then, this would help answer that as well. So does anybody have any direct questions from the homework that they'd like, to go over? Yes, Hayden.
The first question on the homework with finding the intersection of the union, I kind of had some trouble with that.
Sure. Yeah, we can definitely look at that. Okay, so the first question, which didn't have a number, but that's fine. So we're given 3 sets A, B, and C, and I'm going to write them all out just in case we don't have them pulled up here. So set A is going to have the elements, and that's a curly brace here, which I'm...
Wait, sorry, not that one, 55.
55, the first number one. Okay, gotcha. No problem.
My bad.
No worries. All right, so we'll just jump to that one then. Okay, and if we need to double back to the first question, we can absolutely do that. Okay, so question 55, also still on union and intersection. But this one is, we're taking what we learned from the lecture and kind of extrapolating upon it a little bit. So we're now dealing with intervals, but an interval is really just a set of numbers, right? If I give you the interval, and in this case, the first interval is from -6 to 2, right? So we're going to call this I with a subscript of 1, just to denote that it's going to be different. So we have I1, this is from -6 to 2, not including the endpoints. But again, we can consider intervals to be sets of numbers because what's going on in this interval? Well, we have the numbers, for example, -5, -4, -3, so on and so forth. Those are all elements of this set. Intervals and sets are essentially, they're very similar and you can think about them in the same way. So that's our first interval. And our next interval that we have, which, again, denoting with a subscript here of 2, this is from 2 to 10, where we're including 2, but we're not including 10 here. So the first thing that we have to do, and the question says find the union and also the intersection of the two sets. Now, whenever we're dealing with intervals, just like we talked about last time, it's very, very helpful to give yourself some kind of visual representation. And when we're dealing with intervals, visual representation generally means put it on the number line. See what it looks like when it's actually on the number line. So that's the first step that I'm going to take here. I'm going to just draw myself a number line and plot the points here and see what they look like. Just for simplicity's sake and for readability, I'm going to use blue for the first interval, and I'm going to use red for the second interval, just so we can actually see what's going on here. Okay, so the first interval is starting from -6. So we're going to be right over here, and we go up until we hit 2. Right? So we are not including the endpoints here, which means what? What kind of circle do I need on -6 and also on 2? Hayden, sure.
An open circle?
Open, yeah. So we're going to put open circles on -6 and 2. Again, we know this because parentheses, right? Parentheses mean we're not including those endpoints. So we're going to put open dots to represent that. So it's going to be all of these numbers here between -6 and 2. And now what we also need is we need to plot the next one. So we're going to plot the second interval, and this is from 2 to 10. So 10 is going to be somewhere over here. And we know we're not including 10, but we are including 2. So I'm just going to put an overlapping closed red dot on this one. Again, we understand from before that we were not including 2 from the first interval, but we are now including it in the second interval. And so we're talking about all of these numbers now from 2 to 10. So again, the first question says, find the union of the given sets. So what does union mean? Remember, we have to find this distinction between union and intersection. Yes, Chris.
A union would be where the two sets join together, and I don't see one here.
Okay, well, you are definitely correct. Union is where we're taking our two different sets and putting them together. We're just, connecting them together. We're taking all of the elements from one set and putting it into the next set, right? So if our first set here is going from 6 to 2, and then the next set is going from 2 to 10, we can actually just say then that the union, and we'll actually use this with the proper notation here. So the first interval unioned with the second interval, well, this should just be the entirety of from -6 to 10, right? Is there a single element? Is there a single point here that's not going to be included? Well, the only point that might not be included would be 2, right? Because again, 2 right here, that was our problem point for the first interval. 2 was the one that we weren't including, but notice we are including it here in the second interval, right? If we think about it again, just in terms of sets from the first question, so the one above it, the very first homework question, where we were just dealing with, just strict elements, we can say then that, okay, well, 2 is not an element of the first set, but it is an element of the second set. And when you're dealing with unions, you only need it to be an element of either set. It doesn't need to be found in both, just needs to be in one or the other, right? So because we are including 2 here in the second interval, that means that all of these points, except for the endpoints, -6 and 10, are going to be included. Right? -5 is definitely part of our new joined set that we created. It's just the same as 3 or 4 is definitely going to also be part of it. And again, the only problem point that we might have had, which was 2, we know that we're getting for free because of this bracket right here. So we can then say, okay, well, our new interval here is going to be from -6 to 10, where we are not including those endpoints. So again, parentheses here. Does anybody have questions on this in particular? I know this can seem a little strange when we're not dealing with, strict sets. We're dealing with intervals here. But again, the idea is very similar. Yep, Chris?
I always like to tell myself when you're unionizing sets, you're basically adding them together like a little family. It kind of helps me remind me of exactly what we're doing when we do this.
Yeah, and however you need to conceptualize it, totally fine. So in this case, yep, we're just taking one interval, we have a second interval with it, and we're just smushing them together, right? We're just taking the two intervals and putting them together. And in this case, because they connect at the number 2 here, specifically at 2, we can actually just take our two different elements. So again, the other representation of this, if we substituted in for the first interval I1, so this was originally -6 to 2, unioned with the second interval, which was from 2 to 10. We see here that we would essentially get the same thing anyway, where we can actually go ahead and just get from -6 to 10 because of this union. We are trying to just put the two pieces together, and because of the fact that we are including the number 2 here because of this bracket, we're good to go. It just comes in as one streamlined just interval from -6 to 10. Again, the only possible gap that would have been here was at 2, but we don't have that gap anymore. Any questions? Okay, great. So I actually do want to probably revisit the first question, but before we get to that, because I just want to make sure we're all good with unions and intersections, does anybody have any other questions from anything else regarding the homework? Yes, Alicia.
85.
85, yes, 85 is a bit of a tough one. So 85 is all about exponent rules. This was at the tail end of the lecture. So let's go ahead and take a look at this one together. 85 is a fraction. So we have x times y to the -3rd power and z to the -2 power all over x squared, y to the -4th, and z cubed. And this entire fraction here is all to the -3rd power. Okay, so there's a lot going on here. And in fact, when we were talking about orders of operations, everything still holds, but there's not a lot of different operations going on that we really have to discern between. So the good news is we don't really have to concern ourselves with that. If we were talking about order of operations here, we see that we have parentheses, we see that we have an exponent, and we have multiplication, all and division also going on, right? So the first thing that you would do if everything wasn't all being multiplied is you would try to see, okay, well, what's going on inside of the parentheses, right? We're dealing with PEMDAS, so parentheses are coming first. So you're looking inside of the parentheses first to see if you can simplify anything, right? So we look inside this and we say, okay, well, if we're trying to simplify, we see that we have these corresponding pairs in these fractions, right? We have an x on top and we have an x squared on the bottom, right? We have this y to the -3 being divided by y to the -4. And same thing over here, we have the z squared over the z cubed, right? So what we can think about this is we can actually consider this as 3 different pairs of numbers. We have the x over the x squared, the y to the -3 over the y to the -4, and the z to the -2 over z cubed, right? And then once we finish evaluating what all of that comes out to be, then we can take care of this -3 that's on the outside. Now, in truth, and if we have questions about it, I can absolutely go back and show you. In truth, it really actually won't matter whether or not we take care of the -3 on the outside first and apply that exponent inside, how we need to apply it correctly, or whether we go ahead and simplify everything on the inside of the parentheses first. Now, in the best way for most students is to simplify as much as you can and then handle the exponent on the outside. But again, if you handle the exponent on the outside first, it's not going to kill you. It's just going to make things slightly more challenging. Okay? So what do I mean by separating things into pairs? Well, because everything is being multiplied, right, we just have, one term over one term. Well, if everything is being multiplied, we can actually break up this fraction into 3 different fractions just being multiplied against each other, right? This is the same thing as x over x squared times y to the -3 over y to the -4 times z to the -2 over z cubed. Right? This is all I did is I just separated things into the corresponding parts, the like terms, the things that we're, looking to match. And in truth, if you went from here up to, upwards, just to backtrack, then
What's a case race?
Case of beer, you have to finish it in a certain
Caroline,
amount of hours. I didn't purchase it when I went to Halloween.
Perfect, thank you. Okay, so again, in truth, if you went backwards, we can see that it's really just the same fraction, right? We know how to multiply fractions now. You would just multiply across. So your numerators would just be x times y to the -3 times z to the -2, and that's exactly what we have up here, and similarly for the denominator, right? So the reason that I broke this up is because now we can actually examine what's going on, and now we just have to look at our exponent rules. Now, the first thing, we're going to take x over x squared and see what that comes out to be. But the first thing that I want to note is, what is the power of x? What is this hiding power right here? What's the hiding power for any number if you don't see the power? Kirsten?
1.
1, yeah. If we're talking about any number, and as long as the power isn't represented, if it's hiding, if we're just talking about like 7, for example, it's 7 to the first power. That 1 is implied, right? So we know that this x is going to be to the first power. So all we now have to do, we now know the powers of the bases here, and we know the operation, right? The operation is division. So using what we learned in the lecture, we just have to figure out the correct way to handle these exponents. So what do we do here if we have x to the first being divided by x squared? You don't actually have to tell me the answer, just tell me what my process is. What am I going to be doing? Somebody other than Chris. Chris has answered quite a lot for me. Yoav, yeah, help me out.
Don't you subtract 1 from the 2?
Yeah, exactly. So what we're going to do is we're going to keep the base the same. So our base here is x, right? And now the key part is our bases have to match. So as long as we have an x and another x, we're in business. If we had an x and a y, we can't do this, right? This is why we separated things into the matching variables. So we have x being divided by x, so we can go ahead and proceed. So we know we're going to have an x for our base. And just like Yoav said, what we're going to do is we are going to subtract our exponents. So we have 1 minus 2 here, right? And in truth, we know that that's just going to be -1. So we'll handle that for a second. We're just going to table x to the -1 and proceed to the next one. So now I have y to the -3 being divided by y to the -4. Who can help me out with this one? Kirsten, sure.
+1.
Yeah, so what we're going to do is we keep our base, right? So the base is y. We have -3 minus a -4, right? So because it's minus a negative, we know that negatives cancel in pairs. So we know that this is going to be a positive. So we have y to the -3 plus 4, which is just y to the first power. Oops, dropped my pen. There we go. So y to the first power, and I'm just going to omit putting the 1 there, but obviously we know it's to the first power. And now I'm just going to do the last one myself. So we have z to the -2 over z to the over z cubed. So we have z -2 minus 3. And now when we have a negative and we're subtracting a positive from it, it's just going to become more negative. So this becomes -5. And remember, we have this -3 for our exponent applied to the entire parentheses here. So we have now simplified as much as we can inside of the parentheses. Now what we're going to do is we're going to apply this exponent, right? And if we remember, what we're going to do to apply this is we're going to take this exponent and apply it to every single piece inside of the parentheses. So what that means is we're going to have x to the -1 to the -3. Then we're also going to have y to the first power to the -3. And lastly, we're going to have z to the -5 to the -3. And now we just, again, have to think about what our exponent rules say. If we have a base raised to one exponent, raised to a second exponent, how do we handle that? What's our process going to be here? Haley, can you help me out?
You would add them.
Add them. Okay. So keep in mind here, for division, we subtracted, right? So what do you think then would addition correspond to?
You would add the exponents, right?
Yeah,
Like-
no, I understood what you meant. Sorry, I was just leading you somewhere else. So what I was saying is we had, just think about this term right here, right? Our process was we had a variable being divided by itself, right, by another variable, and we subtracted the exponents because of division, right? So what we, yeah, sorry, go ahead, Haley.
Oh, because of multiplication.
Yeah, so exactly. So what we're going to do here is we only add the exponents when the bases are being multiplied. So here we don't have bases being multiplied, right? Our situation's a little different. We have one base raised to an exponent raised to a second exponent. So we have to do something a little different instead of just adding the exponents. What do we do to the exponents instead? There's only 3 options here. So there is subtract, which we did before from the division. There is add the exponents, which we do when it's multiplied. And the last option, Katrine?
Multiply them?
Yeah, exactly. So we have one exponent raised to another exponent. We multiply the exponents. So we have x to the -1 times -3. We have y to the first power times a negative, oops, that's a 3, times a -3. And then lastly, we have z to the -5 times -3. And now what we just have to do is just clean this up, and we should have our final answer pretty soon here. So x to the -1 times -3, well, 2 negatives when you multiply are going to cancel out, right? So we have a positive number, so this is going to be x cubed. Next, we have y to the first times -3, so this is going to be y to the -3. And last but not least, again, we have 2 negatives being multiplied. We're going to get a positive, so we get z to the 15. And there's one last step here, and if you got to this point right here, this is an acceptable answer just for this homework because I didn't put any other directions here. But there's one last step that in general we should get in the habit of doing. We shouldn't leave negative exponents. Negative exponents in general are not something that we should leave. So what I mean by that is, okay, well, we can't do anything with the x cubed, right? X, that's a +3, we're going to leave it here. Same thing with z to the 15, right? But what do we recall from the lecture a negative exponent is going to do for us? What happens to that base? Erin, yes, please.
You can flip it. You can do the reciprocal of it, so it would be like, so if, I don't know how to like.
No, you're doing fine.
Without,
you're absolutely correct.
So
Keep
you
going.
would put it in the bottom of the fraction, and it would be y to the 3rd.
Yeah,
so
exactly.
X to the 3rd, z to the 15th over y to the 3rd.
Perfect, exactly. And this would be your final answer. So just to examine this one more time, a negative exponent, what this means for us, right? If we had, I'm just going to pick a to represent any number, and if we had a to the -1, what that means is it becomes the reciprocal, right? We just flip it on its head. This originally was a over 1, right? We can make any number just divided by 1 because any number divided by 1 is itself. So we just flip it to be 1 over a, and now this exponent stays the same number except the sign flips. So instead of it being a to the -1st power, it's now just a to the 1st power or just a. Right? So what we did here is we saw we had y to the -3, and just like Erin said, what we're going to do is we're going to flip it, so we're going to make it its reciprocal, which is 1 over y, and then the sign of the exponent changes, so instead of it being a negative cube, it's now just a +3, right? So we have this y cubed on the bottom of our fraction here. Okay? Any questions with this? Again, the idea here was just a lot of utilizing our exponent rules. This was definitely a tricky one. Probably not something that I would put on your quiz because it takes a little bit to get through. But again, the ideas are you're just matching the variables up with each other, use exponent rules to simplify, and then take care of that -3 exponent on the outside. Yep, Chris?
Well, would this be something we could see on like a midterm or a final exam?
No. This is, generally speaking, my midterms and final exams are going to be like genuinely fairly challenging. Now I don't mean this to scare you guys by any means, because I have a way to handle that. This is, again, like I said at the very beginning of the class on syllabus day, I've only ever had one person fail my class ever. Right. When I say that the tests are supposed to be challenging, they are very much going to be challenging. And I don't consider this to be I don't consider this to be the final utilization of exponents. This is essentially just determining whether or not you understand how to use your exponent rules, but the midterm questions are designed to basically take this sort of concept and roll it in with other concepts. But
I
we are a
understand.
long
So
ways off from the midterm, so I wouldn't worry about that.
yeah. So we're going to be building on this. So this is the foundation of what a exam problem would be. So
Correct.
I got it.
Yeah. So again, these are what are known as the P chapters. These are the introductory chapters of the textbook, at least for the 3rd edition. So this is all just kind of to give you the necessary tools to build upon, so that when we get to the chapter 1 and beyond, you have all the abilities that you need to adequately deal with the problems that come up. Okay. Any questions regarding this in particular? Just want to make sure we're good with the exponent rules, specifically this last step here where we took the y to the -3 and made it a division of y cubed. I just want to make sure we're all good with this. Okay, great. So with that being said, again, we can definitely jump back to the homeworks, but I'm sorry, the homework questions, if anybody has any other questions with that. But I just want to make sure that I touch on a couple other things, that I had prepared while I still have time here. So I'm just going to go ahead and clear this off. So talking about sets, just going back to sets regarding unions and intersections, there's one thing that I want to touch on here that's kind of expanding upon what we were talking about, right? So we discussed the idea of the empty set, right? Empty set is noted like this, where you have kind of a circle with this line through it. Empty set means it is the set that has no elements inside of it, right? Just a very common mistake that I see a lot of students make. We've kind of gotten in the habit of using curly braces to denote sets, right? Just for example, the very first homework question, right? We had this set with the curly braces of 0, 1, 2, 3, and those were its elements. Please do not put curly braces around the empty set. This right here, this is the empty set, okay? If you put curly braces around this now becomes the set of the empty set, which is something very different and something far more abstract and not for this class, okay? This is something that you would see in higher level math classes like real analysis or topology, but definitely outside the scope of this class. So all I'm saying is just make sure that you're just leaving it as just the circle and the dash going through it, okay? So with this concept of the empty set, what I want to look at is, let's consider a set here. And again, I'm just going to pull a random set, the same one that we had from the first homework question. So I'm going to have A, and let's give it some elements here, where the elements don't necessarily matter. I'm going to say A, B, and C, right? Okay, so we have this. And again, we have our empty set. So my question for you guys is, what happens if we union these two sets together? And what happens if we take the intersection of these two sets? So what I mean by that is, what is A union with the empty set, and also A intersect with the empty set? So let's look at the union of the empty set, or union with the empty set first. So I'm going to go ahead and erase this and just look at this one. So anybody have any ideas for this? I'm just going to scroll up to show what A is. What does union mean? What do we do with unions? Let's start there. Chris? Yep.
I mean, I feel like we're adding something to nothing. I mean, because the empty set is essentially nothing. Yep. So I think it would just be the regular set, because we have nothing to add to it.
Yeah. So just like what Chris is saying, and just to expand upon that a little bit, Chris is saying that there's no elements in the empty set. Obviously, that's what makes it the empty set. And when you're talking about union of two different sets, regardless if it's the empty set or not, you're taking all of the elements from one and all of the elements of the other and just putting them together, right? So we're talking about all of the elements from set A and all of the elements of the other set, so in this case, the empty set, and we're just going to put them together. But if there's no other elements that are being added to the first set of elements, well, then it's just the first set of elements, right? So whenever you union any set with the empty set, you're always going to get back your first set. So basically what this is saying is, okay, if I have elements A, B, and C, and I'm trying to put some more elements with those, well, there are no other elements to, put with A, B, and C. So I just have A, B, and C back from this operation. And because we know A, B, and C are the only elements of set A, well, we get set A back. Does that make sense? Again, union, we're just putting things together. We're taking two separate sets, throwing them together, mishmashing them. And since there's nothing to mishmash with the first set, well, we just get that first set back. So with that in mind, let's also go ahead and discuss what happens if we intersect A with the empty set. So A intersect with the empty set. What do we get here? First off, before you even take a guess here, what does the intersect operation do? Just in your own words. Raven, do you have a yep?
Don't you just like find the things like the numbers or whatever that they have in common and then like put those?
Yeah, so exactly what Raven said, right? The intersect operation between two sets is basically just finding the things that are in common. If you think about it as a Venn diagram, and I know I put this up in the lecture video, if you had one set over here, another set over here, well, the intersect between these two sets is going to be the part that they have in common, right? So what is shared between them? This is what an intersection of two sets is. So, okay, well, now that we know what an intersection does, we just have to ask ourselves, okay, well, what happens if we intersect A with the empty set? Well, A has some elements, right? Does the empty set have any elements? No, that's what makes it the empty set, right? So if we're looking for things that are in common, is there going to be any elements in common if the empty set doesn't have any? No. So all we're going to end up with is just the empty set back. The reason is because if there's no elements in common, that means there's no answer, right? There's nothing that is going to arrive from using the intersection between a set and the empty set. So we just get the empty set back, and that would be our answer. So notice the difference here. If we take the intersection between a set with elements and the empty set, we get the empty set back. And if we take the union between a set and the empty set, we get the set back, the first one that we started with. I know this can all seem a little bit abstract, and I totally understand if it, might not make sense the first time around, but just, mull it over. And if you have any questions, or even right now, if you have any questions, please feel free to, lob them at me. But the idea here is, just understanding a little bit more about what the operations are actually doing. Okay. All right. So don't worry too much about sets. We mainly, for the remainder of this class, we really don't deal with them too much. It's just a good introduction to them. So if you don't really understand what's going on here, it's okay. I promise, don't panic. This is not going to be the entire semester. We mainly just deal with intervals, but again, keep in mind, intervals are essentially just a form of sets. So just have that in the back of your head. And the last thing that I had prepared for you guys today is I just wanted to do another quick demonstration regarding the exponent rules. So there's two little things here regarding that. So first off, let's say I have 8 times a, oops, sorry about that, my own notes, 8 times a cubed times b, and this is all to the -4th power. And I am multiplying this against a fraction. So my fraction here is 2a over b. and this is going to be to the 12th power. So there's a lot going on here, and again, this is very similar to 85 in the sense that we really have to try to figure out a plan here. So in 85, the one that we just did, we were essentially going to reduce what was inside of the parentheses first, and then tackle the exponent that was on the outside, right? Well, if we look at these parentheses, let's look at the first one, which I'm going to underline here in red, 8 times a cubed times b. Is there any sort of simplification that we can do? Is there any shared common, things here? Any variables that we can, tackle together? Chris?
I mean, we can factor the 8a into 2a cubed squared.
Don't even worry about factoring. Factoring is
that's not going to help us. That's not going to help us.
Correct.
That's about all.
Yeah, exactly. So point is no, there's nothing that we can do here, right? A and B are two different variables. We can't combine them together without knowing what A and B are. So without having that information, okay, well, we can't do anything here. So the parentheses in red, definitely out of the question. And same thing for B, or, I called it B, sorry. Same for the one in blue here. We realize that there's really no simplification that we can do in this parentheses as well, right? 2A over B, we don't know what A and B are. So without knowing those values, we can't simplify the parentheses. So where does that leave us? Well, that leaves us with handling the exponents on the outside, right? The -4 and the 12, those exponents, if we can tackle those, then maybe we can finally do this multiplication, right? Notice that we can't multiply the two parentheses against each other just yet because they have different powers, right? This is to the -4th power. This is to the 12th power. Because the powers are not the same, we can't multiply them against each other. However, if the powers were the same, then we could. But that's just not the case here. So who can help me out? Let's deal with the parentheses in red first. What am I going to do with this -4? Somebody other than Kirsten. Yeah, Maggie.
You're going to distribute the -4 to the 8, the A, 3, and the B?
Yeah, great. Okay, so we're going to have 8 over here to the -4 power. We're going to have A, and what happens to the A when we have A cubed to the -4th? What's our plan if we have a base raised to an exponent to another exponent? Maggie, you can go ahead and answer that one since you were already there.
Oh, you add them, right?
Close.
No, you multiply them?
I'm sorry?
I said you multiply them?
Yeah, you multiply them, right? So what's 3 times -4?
-12.
Perfect. So we have A to the -12, and then similarly we have B to the 1st power, right? It's a hiding power of 1. So 1 times -4 just gives us -4. So we have B to the -4, right? And this is, I'm just going to keep it in parentheses here, just so we can, keep everything organized. And now next up, we have a fraction to raised to an exponent, right? We have 2A over B raised to the 12th power. How do we handle a fraction being raised to an exponent? What do we do with this exponent now? Yeah, Matthew.
You just distribute it to both sides of the exponent.
Of the fraction?
Yeah, of the fraction. That's what I meant.
Yeah, exactly what Matthew said, right? So we're going to take our exponent and we're going to apply it to both the numerator and also the denominator, right? And now notice we have two different terms in the numerator, so we have to apply the 12 to both different terms in the numerator. So the 12 is going to be applied to the 2, the 12 is going to be applied to the A, and then the 12 is also going to be applied to the B, right? So, okay, great. We're going to do that, and hopefully that should simplify things a little bit. So, oops, sorry. So we have 2 to the 12th, and then A to the 12th, and this is all being divided by B to the 12th, right? So B to the 12th. Okay, so we're getting closer, right? Now we have two different terms that are both to the 1st power, right? This exponent hiding here for the parentheses to the 1st power. This parentheses is also to the 1st power, right? Because we distributed the exponents, the -4 and the 12. So as a result, because these now have the same powers, both of these parentheses, we can now multiply them together, right? Well, we're actually going to do just a little bit better than that. notice how, and actually Chris brought this up a little bit ago, notice how 8 is really just a power of 2, right? What is 8? 8 is 2 times 2 times 2, right? 2 times 2 is 4, times another 2 gives us 8. So we can actually rewrite this as 2 cubed. And now this is actually going to help us with evaluating what this comes out to be. So I'm going to go ahead and rewrite 8 to the negative 4 as 2 cubed to the negative 4. And then also a to the negative 12, b to the negative 4. I haven't touched anything else, right? That was the only thing that I've changed so far. So 2 to the 12th, a to the 12th, and b being divided by b to the 12th. Okay. So now we can go ahead and proceed here with the actual multiplication in the same step. What I'm going to do is I'm going to simplify this. Just like Maggie told us earlier, what we do when we have a base raised to an exponent to another exponent, we multiply those exponents. So we know that we're going to get 2 to the negative 12th there, right? So we see here, this is going to be 2 to the negative 12th. This is going to be still a to the negative 12th. And this is b to the negative 4. And there's one last thing that I'm going to do here before I multiply them. And what I'm going to do is notice that I have a b in the numerator, right? If I consider this parentheses here, which I'm going to underline in red one more time, if I consider that one as a fraction, well, notice that this is all essentially being divided by 1. So you can consider that b is in the numerator currently. Well, if I multiply these together, this is going to get a little bit messy. So why don't I also go ahead and bring this up to the numerator? Well, how would I do that? Using exponent rules, how do I bring something up from the numerator, from the denominator to the numerator? It has something to do with what we talked about with the very end of question 85. So if we remember from 85, what we ended up with was we had y to the negative 3, and with Aaron's help, we made it 1 over y cubed, right? And yeah, Monique, try to help me out here. What am I going to do with this b to the 12th?
You make it into b to the negative 12th power?
Yeah, exactly. And then we bring it up top, right? So we see here that we can actually do it either way, right? If we have some number to raised to an exponent, we can always just flip it back, right? We can bring it to the numerator. We just have to make sure that we negate it when we bring it to the numerator. So great job. That's exactly what we're going to do. So we have 2 to the 12th, a to the 12th, and then b to the negative 12, right? We brought it up to the numerator and we negated the exponent. Okay, well, now let's just multiply the like pairs, right? We have 2 to some exponent. We have 2 against some exponent. So I'm just going to put those in their own pair together, right? So I'm going to have 2 to the negative 12 times 2 to the 12th. Again, pairing things together, I have a to the negative 12 times a to the 12. That's an a, not a 9. Sorry about that. And last up, we have b to the negative 4 times b to the negative 12. Okay, well, let's go ahead and just clean this all up. 2 to the negative 12 times 2 to the 12th. What happens? What's our process when we have the same base being multiplied against each other and, different exponents? What do we do with our exponents? Kirsten?
Don't you add them?
Yeah, so what's negative 12 plus 12?
0.
Okay, and so we have 2 to the 0, but what is any number to the 0 power? Yeah, Nico.
1.
Yeah, any number to the 0 power is always going to be 1, right? We saw this. This is just one of our universal truths. A to the 0 is equal to 1. So because Kirsten helped us when we had 2 to the negative 12 times 2 to the 12th brings us to 2 to the 0, we know 2 to the 0 is just 1. So great, we have a 1 here. And hopefully you guys are all okay with me just omitting that 1, and I'm just going to move on to the next piece. So we know that that one is done. Okay, similarly, we have a to the negative 12 times a to the 12th. What's going to happen here? Well, the exact same thing, right? We have a to the negative 12 times a to the 12th. We add them because they're being multiplied. So we have negative 12 plus 12. That gives us an exponent of 0. So we would have a to the 0. But a to the 0, again, it doesn't matter what number it is. It's always going to just be 1, right? So far we have a 1 times whatever is going on over here. And we just need to finish this up. B to the negative 4 times B to the negative 12. Again, we know we are going to add them. So we see that we have B to the negative 4 plus a negative 12, which is the same thing as B to the negative 4 minus 12. And so we can wrap this up as B to the negative 16, which now we're just going to go back. Again, remember I said try not to leave negative exponents. So we're just going to leave it as this. And this would now be your final answer. Okay, I know that took a lot to get through. There was a lot of different steps that we had to take. But again, the ideas are all there, right? It's the same ideas that we've been discussing, from the lecture and that we've been discussing all day today. We're just going to take our exponents on the outside and apply them to each single piece inside the parentheses, right? We do that only after we try to simplify the parentheses, but in this case, we couldn't simplify anything. So we just went right to that step. Then what we did was a little bit of math magic, right? We saw that 8 was really the same thing as 2 cubed. And the reason that we did that is because I wanted to try to combine this 8 with this 2 over here. Notice that we wouldn't be able to do that otherwise, right? If I had 8 to the negative 4 times 2 to the 12th, I mean, good luck trying to figure this one out, right? We have to just try to figure out how to manipulate the numbers with the exponent in mind, so that way it becomes a little bit easier and we can just use our exponent knowledge to simplify. So with that being said, we were able to do that. We made the 8 into 2 cubed. Again, we noticed our rule here. If we have a base raised to an exponent to a second exponent, we just multiply them. So that's how we got this negative 12 here. And when all is said and done, we saw that we got 2 instances of some number raised to a 0, which is always going to be 1. And the only thing left over was b raised to the negative 16th. So 1 over b to the 16th. Any questions? All right, guys, I release you. I'm going to go ahead and stop the recording here. Again, you're going to get an email just saying that, great, office hours, you're probably going to get a Teams invitation for it. If you don't, just check your Teams because it should be listed there on the calendar. And this recording, I will try to actually have up at some point tonight. Okay, so otherwise, have a good one. Next lecture will be up tonight, and I will see you on Wednesday.
Thank you.
Thank you.
See you Wednesday.
Have a great
Thanks,
day.
Professor. Have a nice day.
Thank you.
Thank you.
Thank you.